So maybe we can join, wait another minute to let people join from the other sessions. Hi, Claudius. Okay, so at this point, I would start. Welcome, everybody. I'm Guido Salvaneschi from the University of St. Gallen. I'm chairing this session on validation and verification. We are going to have all the presentations in a row. So that's 5 minutes for each presentations. And then we will have all the discussion in the second half of this 1 hour slot. I would like to invite the audience and then the other speakers to type your questions in the chat here. And then we can go through them in the rest of the slot. So the first talk is a journal first paper from Transactional Software Engineering. The title is Control and Discovery of Environmental Behavior. Our speaker is Sebastian, and if you want to start sharing your screen, then the stage is yours.
Okay, thank you. Just let me know if you're seeing now the presentation or my notes. I don't know which. Can somebody just let me know?
No, nothing for now, right?
You're not seeing anything?
No.
Fantastic. What's going on? So, share screen. Okay. So I have this dialog box up. Okay. That should do it now. Let's see. How about now?
Yes, it works.
Yes, it works. Okay, so you're seeing my slide, not my notes. Cool. Okay, so let me start by saying I'm Sebastian Urchitel, and I'm presenting work I did with my colleague Victor Braverman, Nicolas Dipolito, and Neil Peterman. So an important ability of self-adaptive systems is to be able to autonomously understand the environment they're executing in and to use that understanding, that knowledge to control the environment in such a way that the goals of the adaptive system are achieved. The usual way of doing this is in a two-phase procedure. In the first phase, what the adaptive system tries to do is to understand the behavior of the environment by probing it. It acts on it, it senses its state, possibly resets the environment multiple times to be able to try different things out. and to build up this behavior model. And once it has a behavior model, it tries to derive a control strategy that will succeed in providing the goals. If that strategy exists, then essentially you have a controller for the environment. But if that strategy doesn't exist, then you can report that the goals are unrealizable, and then you can do other things, mitigate it in different ways. So this is the discover and then control approach, which is essentially guarantees that eventually either the goals are satisfied because you've discovered and you've seen that you can control the environment, or you eventually report that the goals are not realizable. So, just for an example, if you're building a bookfinder system that's going to integrate at runtime with some kind of service, book loan service, which it doesn't know, it just is using some kind of service discovery feature. So it will, of course, know what the API is for the service it's going to link up with it, but it doesn't know what the protocol is, and it has to learn the protocol to actually achieve the goals that it wants to achieve. So, of course, after this discovery procedure, in which it might infer that this state machine that you see here is the behavior of the environment, then it can indeed infer a strategy for achieving the goals. Note that in this model, in state number 3, you have a choice between unavailable and available, which are uncontrolled events. These are events that the service is going to return, but the adaptive system cannot control. It doesn't control if the book is available or if it's unavailable. So it needs to be able to deal with these situations to achieve the goals. But of course, if they're uncontrollable, then in the discovery phase, what you might have is that the environment actually never offers this unavailable action and never lets you understand what is the environment behavior should you get one of these events. So if there are uncontrollable events, then of course the discovery phase isn't guaranteed to finish. So the environment has uncontrollable behavior. It might have adversarial behavior that deliberately prevents you from actually discovering what its behavior is, and you never go on to the next phase to be able to derive a control strategy. So this discover and then control approach doesn't really work, and what we have is, and this is our proposal, is an approach that does simultaneous control and discovery of the environment. So we have 3 kinds of guarantees that we provide. One is that we will eventually discover enough information to know that the goals can be satisfied and indeed satisfy them in the environment, or discover enough information that to be able to report that the goals are impossible to satisfy, or the third option, which is to not be able to finish the discovery phase, but be able to guarantee that while that discovery phase does not end, the goals are being satisfied in the meantime. So even if you don't achieve full discovery, you're winning anyway. So how does this work? Well, we use an iterative process in which we have a model of the environment which is partial. It's an underspecification of what the actual behavior of the environment is, and we use controller synthesis for these partial models described as modal transition systems to reason about that behavior and to be able to essentially either in every step of this iterative process take an action on the environment that either increases the knowledge we have about the environment or brings us one step closer to achieving our goals. So iteratively, either we will eventually get enough knowledge, or if we don't have enough knowledge to decide if the environment is controllable or not, we will at least be satisfying the goals in the meantime. So to finish off, what we're doing is providing a technique that supports adaptive systems in adversarial unknown environments to be able to understand the environment and then control it. But we do these 2 things together. We control and discover at the same time, and we use modal transition systems to describe partial behavior, partial knowledge of the behavior, and control synthesis to decide what the right actions are. So thank you very much for that.
All right. Thanks a lot. I would then switch to the next speaker, who is Claudius from the Technical University of Munich, and he is presenting reliable test infrastructures in automotive testing setups. And you should be able to share the screen, and the stage is yours.
Yep. Sorry, I was just typing the question for the other talk. So now this is the slide set. Okay, perfect. So, yeah, my talk is software engineering practice paper that we submitted, and as you can see from the title, it's called Unreliable Test Infrastructures in Automotive Testing Setups. And this work was a joint work from the Technical University of Munich, where I'm a researcher at, and Matthias Fruth, mainly from Fastronic. And Fastronic is a leading company for test automation in the automotive domain. So for everyone of you who might have enjoyed, just like me, the talk from Elaine Bayunker, yeah, this is something that I guess she would have liked because this is a actual research, so to say. And the question that the Fastronic regularly faces is that, well, in theory, if a test case fails, you've found a fault in the system on the test, but practically this is not necessarily the case. Actually, yeah, the hustle begins to answer the question, what went wrong? And in particular, if unreliable test infrastructures are involved. So what are infrastructures? Basically everything that is involved during testing apart from the system and the test, and in particular in the automotive domain, this is hardware in the loop test beds or test benches, basically, and everything that you need to control those, to set the state, to charge the batteries, to observe whatever is happening on the bus system, and everything that you need to simulate, for example, all the parts that you have not physically there. So the system and the test are basically control units, electronic control units, and the test infrastructure is everything around that you need for testing. What we tackled in our contribution here is, first of all, to answer the two questions posed here. So how many invalid test failures are produced during automated test execution in automotive system testing? And how many of those invalid test failures can be ascribed to unreliable test infrastructures? The practitioners knew in advance that they have a problem, right? So they have a problem that they face many test execution failures that do not reveal any fault in the actual system of the test, but anything else that fails. And in fact, we came up with we looked into 4 concrete projects for which the numbers are presented here. So the key takeaway is that up to 91% of all failed test executions are actually invalid. So of the category 2 and 3, which is here the test infrastructure issues or the other causes, depending on the project. So in one project, at least from the label data that we have, 26% were linked to code defects, but in the others, it was more or less 10 or 9%, which would be the valid test failures. So the test failures that you expect, that you want to find. And the unreliable test infrastructures, meaning kind of flaky test behavior or sporadically failing tests due to anything that occurs that is out of your control or that has to do with the, let's say, unreliability or irrobustness of the test infrastructure, they amount up to 27 to 53% of all failed test executions. And as I think I still have some time, I might add here, or you might wonder what other causes are and how we distinguish them from test infrastructure issues. Well, test infrastructure issues, as I mentioned before, is everything that we consider the sporadically failing things that are out of your control, like defective components, faulty simulation models, maybe unstable software tools. And the other causes are rather the operator-dependent issues. So things that you could have prevented potentially if the communication was perfect between all the stakeholders. So test case implementation problems, incorrect or outdated test specifications, configuration mistakes, assigning a test case to a test bench where, well, it cannot run because something is missing there. So that's why we just called it other causes, because we needed to gather somehow everything there. Okay, so maybe it's interesting again, also what we do now, as this was a preliminary study. The main problem remains. So we have many invalid test failures and only limited time for the test experts to look into that. And what we're currently trying to do is to predict or automatically classify the test case executions into those three categories, or well, sometimes more categories that distinguish the different types of failures that you can encounter. Yeah. So that was my quick wrap up. If you're interested, I'm happy to take some questions and to join the discussions with you later. Thank you for joining the session, and yeah, I'm looking forward to the discussions.
All right. Thanks a lot. And the next speaker is Ellen from Northeastern. She's talking about Nessie automatically testing JavaScript APIs with asynchronous callbacks. And the stage is yours. This is a technical track paper, by the way.
Cool. I'm just going to share my screen. All right. Can you guys all see? Okay. Okay, so hello. My talk's about testing JavaScript APIs with asynchronous callbacks. So this is joint work with Sebastian Harner and Michael Prattle at the University of Stuttgart and my advisor, Frank Tipp at Northeastern. So we set out to figure out how do we generate tests for JavaScript APIs with asynchronous callbacks. So I'll just break this down, a little bit of intro and background at the same time. So JavaScript has APIs with async callbacks. Callbacks are just arguments to functions that are also functions. So here we see an import of a module. So this is just a module that provides extra functionality to deal with the file system. Here we see a call to read JSON from that module. So this is an asynchronous file read. We throw it on the event loop, then we keep going with program execution while the file read is happening in the background because it's being dispatched to the operating system. Then once the file read is done, the callback executes and we see the second print statement. So basically, we have an asynchronous computation. The prints happen not in the order that they appear in the file. So how do we generate tests for these APIs with async callbacks? So we built Nessie, the test generator. It generates the async callback arguments. So that's these functions that are arguments. We also generate nested API calls. So that's where we see another API call in the body of the callback argument to another API call. So here we see output JSON inside of read JSON. So you might be wondering, why do we do that? Well, nesting is more representative of the intended API use, and generating nested tests are more likely to generate sensible arguments. So here's an example. We have a read directory function as part of fsextra. The callback takes two arguments. One is the list of all the files in the directory that it just read. This is the intended use of read directory. So basically, with each of the files, we can do something. In this case, we're reading the file. So yeah, the current JavaScript API testing does not provide this functionality. So ours is the first one that provides both synchronous and asynchronous callback arguments and nesting and sequencing. So I'm just going to walk through kind of the pipeline of the way that Nessie works with an example. So the first phase is API discovery. So that's where we learn a list of all the functions that are part of the API and then represent them with a list of abstract signatures. So that's the number of arguments, and for each argument, is it a callback? And if so, is it synchronous or asynchronous? The second phase is the actual test generation. So the first step in the algorithm is to select a function to test. So in this case, we'll choose ensure file. Then we choose a signature for this function. So in this case, it takes two arguments. The first one is not a callback, and the second one is an asynchronous callback. Then we generate arguments for the selected function and then execute the resulting test. In this case, we observe that the callback is executed. And so that means that when we figure out how to extend the test, we have two valid extension points, one inside of the callback itself. So this is a nested extension, and another after the function call. So this is a sequence extension. So in the algorithm, we choose an extension point randomly. In this case, we'll select the nested one and then repeat through the algorithm again. So select another function to test. Here we'll choose read JSON, pick a random signature for this function, generate arguments for the selected function. And now we extend our previous test with the new call at the extension point. So we just insert the code for the new call that we've generated inside of the body of the callback. And there you go. So that's the full test. We also mine API usages and use that as input to the test generator to generate more reasonable and like realistic examples, but I don't have time to talk about that, but you can ask me about it. So let's discuss the evaluation briefly. We tested this with 10 file system and promise libraries that have asynchronous APIs. So that's just 2 realms in JavaScript that have a lot of asynchronous APIs. We tested the effectiveness of our discovery phase and found that we find with our automated discovery, 62% of documented signatures that expect callback arguments and 38% of those that don't. We also tested the coverage of the library itself and found that Nessie achieves slightly higher coverage than the previous state of the art, but many fewer tests are required to reach this coverage. And then we see a similar trend with behavioral difference tracking. So we see that Nessie finds many behavioral differences, but the differences are found more quickly than with the previous state-of-the-art test generators. So in conclusion, Nessie is a test generator for asynchronous JavaScript APIs that supports both sequenced and nested API calls. We achieve slightly better coverage and behavioral difference tracking than the previous state-of-the-art, but in many few tests. So thank you for your time.
All right, thanks a lot. Just a reminder, please add your questions to the chat on the right, and then we can include them in the discussion later. Then the next paper is towards boosting patch execution on the fly. From the technical track is Samuel here. Or is any of the authors of the next paper available? Let's give them a couple of seconds to, well, apparently not, so we can still postpone the talk to the end of the first slot. So then we move on to the paper, Diversity-Driven Automated Formal Verification. This is a paper from the technical track, and Emily is presenting. So please, the stage is yours.
All right, you see my screen? Okay, great. Hi, my name is Emily First, and I'm a PhD student at the University of Massachusetts Amherst. Today, I'm going to talk about my paper, Diversity-Driven Automated Formal Verification, which is joint work with my advisor, Yuri Brun. This work presents a tool called Diva that leverages the diversity in different models of proofs to verify more properties of software systems automatically than ever before. And with that, I'd like to tell you why you should care about automating the formal verification of software. Formally verifying software is important, especially in high-stakes domains where buggy software can cost people their lives. And so it is critical to prevent that. A promising method for building correct software has been to use programming languages that are designed to support verification, called interactive theorem provers. Coq is a language that we focus on in this work since it is used in many software verification efforts. With Coq, a programmer can specify a theorem about a property of their software and write a proof script, which is a series of proof tactics that Coq uses to attempt to construct a proof of the theorem. You've managed to complete the proof if you're able to get to QED. These interactive theorem provers have already had a significant impact on industry. From using formally verified compilers and cryptographic libraries to building formally verified solutions offered as a service for clients, to providing tools for users to detect vulnerabilities, these are some companies that have been using interactive theorem provers to ensure safety and improve performance of systems. Still, even with the help of an interactive theorem prover, the effort required to write proofs is often prohibitive. Verifying code requires a lot of time and a lot of proofs in proportion to your code. For example, for the Coq verified C compiler CompCert, the proof is more than 8 times bigger than the compiler code itself and took 3 person-years of work. So as a general rule, because of the great expense of verification, virtually all software the companies ship today is unverified. If we can cut down the time programmers would need to spend on writing proofs, that would be a big win, because we'd be making progress towards enabling more verification. Our tool Diva, together with prior work, has reached a new milestone of proving over 1/3 of all theorems completely automatically on the CoqChim benchmark, which is the largest available collection of real-world Coq projects, with a test set of over 10,000 theorems. Following prior work, we use machine learning to model existing proof scripts to perform next tactic prediction. A partial proof script serves as input to a model that has been trained on a corpora of proof scripts, and it can predict the likely next step of the proof. We combine this with search to synthesize complete proof scripts. The question remains, which proof script model do we use? Do we use the one that has the best overall success rate? But what if the particular theorem you want to prove is proven by another model? Our tool Diva explores using multiple diverse models and how to leverage the diversity in those models to enable more verification. Usually with multiple models, you think of ensemble learning. And in a typical ensemble learning setup, you have a set of models that differ in some way, and you consolidate their predictions, and they vote on a single prediction to use. But one of the problems with that is typically the majority of models have to make the correct decision. If only one correctly performs the particular task, the other models will drown it out, and the ensemble will fail on that input. We overcome this problem in the formal verification domain. For the downstream task of generating a complete proof script, we can let each diverse model use search to attempt to synthesize a proof script for a given theorem from scratch. The Coq Proof Assistant can then unequivocally tell us if a proof is correct, and so we can throw an army of models at the problem, and even if just a single one generates the proof, our ensemble can pick that proof out every time. So multiple diverse models and the existence of a proof assistant, a correctness oracle, mean that we don't have to sacrifice proving power. We don't have to choose between models. So what do we vary to create this diverse set of models that potentially prove complementary sets of theorems? Well, we can vary what aspects of the training data we encode, such as the proof script and the kernel proof state, and the learning parameters of the model itself, such as the learning rate and the embedding size. We implement and evaluate these types of variations in Diva. Through these variations, we generate 62 models that together make up Diva. Using the diversity of these models was a big success and allows us to prove 77% more theorems than the single best performing model. And together with the prior tool Coq Hammer, which instead takes a solver-based approach, Diva proves more than a third of all the theorems in CoqGEM, which is the largest fraction to date. To run a bunch of diverse models in series would take a very long time, but we develop a method that instead cuts down the mean time to prove a theorem by up to 97%. And our work strongly suggests that using diversity for improving automated formal verification is fruitful and will enable automating more verification. Thank you.
Thanks a lot. And now we are ready for the last talk of this lot. The paper is Nalin, learning from runtime behavior to find name value inconsistency. And the talk is by Jibesh at the University of Stuttgart. Please.
Hi, everybody. My name is Jibesh, and today I'll be talking about Nalin, which is a learning-based approach to find name value inconsistencies in Jupyter notebooks. And this is a joint work with Michael Paddle, and we both come from the University of Stuttgart, Germany. So let me start by talking about the motivation behind this work. And identifying names in programs are important because they convey the intended semantics of code, and they are important to understand and maintain code. Now, let me illustrate this with an example where a chosen identifier name does not properly reflect a of code or is hard to understand. So here is a code where the developer intends to check if a file called reference.csv exists in the file system and issue a warning if it does not. And during execution, the variable called file gets assigned a Boolean value. And I guess most of us can agree that a more appropriate name would have been file exists or path exists instead of just file. And as a result, the variable name and the value assigned to it does not match. And with Nalin, our goal is to find such name value inconsistencies. So let me show you an overview of how Nalin works with the same example. And our first step is to dynamically analyze such programs and extract variable names and the assigned values and certain other properties. And for this program, there exists only one assignment. And during analysis, we'll extract the variable name, which happens to be file here, the value assigned, which is true in this case, and the type of the value, which happens to be Boolean. We also extract certain other properties about the value, such as the length and shape. For this case, this property does not exist because the type is bool. And next, we combine all this information with different ways of encoding and feed it to a classifier, which outputs a probability with which it thinks a particular name value paired to be inconsistent. So this briefly shows how Nalin works. Let me also show you some results. So our experimental setup consists of 1 million Jupyter notebooks scraped from GitHub, and we could instrument half of them, and on execution and filtering, we obtain 500,000 name value pairs that we use as our experimental setup. And in this talk, I would like to highlight only 2 research questions. The first is the effectiveness of the classifier. And this plot shows the precision, recall, and F1 score of our classifier on the y-axis, whereas which are taken at different thresholds shown in the x-axis. And we find that our classifier attains the best F1 score at the threshold 0.5, and showing that the classifier is indeed effective in finding name value inconsistency. Now, let me highlight the second research question, where we check the usefulness of Nalin with an user study. And for this, we randomly select 40 name value pairs, for which half has been classified as inconsistent by Nalin, whereas other half as consistent. And then we ask developers if they think the name value pairs to be hard or easy to understand from the perspective of maintainability. And we find that for most of the cases, Nalin's prediction matches developers' assessment, and this gives a precision of 80% and a recall of 76%. So this shows the usefulness of Nalin. Let me also show you the kinds of inconsistencies Nalin find, and we check this by selecting top 30 produce warnings and manually inspect them. So these are the 3 types of inconsistencies. The first is misleading name, which happens to be the majority, where this is one such example where a developer uses the variable called name to assign a number. And I guess a more appropriate value would have been probably a string type. The next type is incorrect value, inconsistent. And here, a variable during execution, a variable called prob gets assigned a string corporate, and this leads to the code crashing in the next line. And I hope we all can agree that a more appropriate value would have been a number type. Nalin also produces some false positive. Here is one such example where a variable called dwar has been assigned a path, and Nalin wrongly produces a warning in this case. So this concludes my talk. Thank you very much for listening. Do check out our implementation in the given link in GitHub. Yeah, thanks again, and I would be happy to take questions.
Thanks a lot. And this also concludes the talks for this session, and I would move on to the discussion. There are already some questions that we have in the chat, and I'm wondering what the first question, which talk the first question is about. I think this was for Sebastian. What are the underlying assumptions for this approach, especially about the environment? Is that the case?
Yeah, that's for me. So thanks for the question. So there are a number of assumptions. The first is that we can reset the environment, of course, which is not always the case. It's easier for software environments, but not for cyber physical systems. Perhaps that's more complicated. The next is that we can sense its state. So the environment's capable of giving us some ID consistently about its state, which might be a hash of its internal structures or something of the like. Again, if it's the environment's only software, or it might be an estimation of the world around a robot, for instance. So we assume that, and finally, but most importantly, we assume that the behavior of the environment can be represented as a finite state system. So it's a regular language. So those are the 3 key assumptions.
So maybe connecting to that, the environment in this case is it's a set of facts, or how do you?
So the environment might be in the small example I was discussing, might be a service you've connected to, and that you know the API, but you don't understand its protocol, so you start trying things out and asking what the state is, and And the only thing you need is to get an ID that's consistently returned. So if you return to the same state, you get the same ID. And from there, you start inferring what the behavior of the environment is. It could be something more complex, like a bunch of sensors, which are giving you an abstraction of the physical world too, right? So we use it in robotics examples.
All right, thanks a lot.
So,
Any other
so
questions?
to follow up on my own question here, so you assume a static or somewhat static deterministic environment, or not necessarily deterministic?
So the technique we have implemented assumes a deterministic system. The techniques we use can work with non-determinism, so that would be eventually something that could be dealt with. Of course, that has an additional complexity in terms of computation.
Okay, so we also have in the chat another question. I think this is for Claudius. What are the difficulties in detecting the failures of the test infrastructure at runtime? Can some not be solved during the text execution?
Yeah, perfect question. I totally skipped that during the short talk. So why is that a problem anyways? Well, of course, yes, some of the problems that occur can be remedied during the test execution. For example, by adjusting the test case definition or the specification or how you compose the test case. And yes, in fact, as you can expect, this is industry, so they do not play by the book, let's say. So not everything is as good as you would hope it would be. So this is not rigorously done. For one, it's too costly, and in some cases it's not even possible, because some things you just cannot observe. So you cannot distinguish whether or not some state internally in some hardware has changed, but that has an effect maybe later on in something that you can observe, and that makes your test case fail, even though it's not the actual test goal that is not fulfilled, right? So observability is a problem, and also, well, that it's industry and it's not, let's say, rigorously done. And there are some other things that make it especially difficult, I would say. Again, information is not always available, so some things change, but you don't know about it, you as a tester or as a test expert, and then you just see, okay, something changes and now my test fails, and you need to call people to find out what the problem was. And you cannot encode everything in fixed rules. But yeah, maybe that already answers the question, why this is somewhat difficult.
So you have by now a lot of experience with this industrial, real world cases. What would you say is the kind of solution that one should explore? I mean, is it about tooling? Is it about communication among teams? Is it it's a social problem or a technical one?
That's a multi-dimensional problem, but the ones that, or the one problem that I try to solve now, now that I have looked at many of the data points, how at least to lift the burden a little bit for the test experts who need to decide whether this is a actual code failure, so that they write a bug ticket and then assign it to the actual developers, or contact anyone else, the ones responsible for maintaining the hardware, for example, or the test infrastructure. And of course, it would be best if they would have access to, and if everyone followed the strict protocols. If I change something, I change it back before I leave, or something of that kind. But as this is, let's say, out of our control, we try to use what is there. So the test cases, the test step information that we have, and which test step does fail, which not, and this kind of pattern that rises, at least in our experiments right now, gives us a good indication of what the underlying problem is, without digging too deep into all the process logs that might be available or might not be available. Yeah, so that is kind of the idea that we are looking into right now. So using as least information as possible that you have readily available, like the history of executions and how the tests were executed, and by that kind of judging, okay, where might the problem lie?
Okay, thanks a lot. So if there are no other questions for now to Claudius, then I would go through the quite long list of questions for Jibesh. So maybe you can start from how did you build the validation set?
Thanks very much for the questions. So the first question, to answer here is that we created the validation set by splitting it randomly. So 80-20, so 80% we use for training and 20% we use for validation. I hope this is the question.
Sorry, I meant more like, how did you label your validation set?
So
like, because presumably, yeah, so you had things labeled as, yes, this is an accurately determined inconsistent pair, or like this is actually not inconsistent.
Right. Okay.
I was just wondering how you built the validation set.
Okay, I understand. Yeah, so I didn't go through that part in this hot talk. So what we did was that we extracted name and value pairs by dynamic execution. And then we created negative examples or pairs of name value pairs which are inconsistent. And we did it with an approach called type guided approach. This is what we call it. And what we do is effectively is that we combine names, variable names, and values which do not occur together in the data set that way. So we try to match names and values that do not occur, and then we label that this is an inconsistent pair. And this is how we artificially generate them, because we assume that whatever we extract are correct. I hope. So does that answer your question? And then we split it. Okay. So
there is also a very interesting question on the follow-up work on synthesizing the name, right? So now you're tagging whether the name is good or not, and you could generate.
Yes. So right. So so the reverse could be done effectively. Yes. But we didn't, of course, try it here. But I think it should be possible where so here we try to check if a particular name and values are inconsistent with a classifier. But theoretically it should be possible also that we use the value and try to generate names that goes with that value. I hope. Okay, thanks. The next question is, are there categories and name values that could be statically? Yes, of course. There's a large body of work where mostly linters, for example, which we use in IDs, where they use static analysis to find such kind of inconsistencies. But here in our work, we mostly focus on using dynamic analysis.
And I also want to have a look at the last question. Yeah.
Yes. And do you have any plans for type consistent non-primitive types? Actually, we do. Also include non-primitive types, if I understand correctly. So we don't just focus only on primitive types. So we also, what we do is that we look at the top 10 types that we find in our data set. And this includes, I think, data frames and also series. But do you write data frame versus series? Does it mean anything else, or?
Oh, I was just wondering. So, I mean, like, I've definitely messed that up before when I'm writing data processing code, where like I have, a series and a data frame, and then you get them mixed up. I thought like maybe there were type inconsistencies that were more common in Jupyter notebooks, because that often has a lot of like pandas heavy stuff.
Right. Yeah. So the thing is that we do not combine them. So whatever we get, let's say if a type is a series, we say, okay, so this name goes with a series and this name goes with a data frame. So if developers most of the time use a particular name, let's say DF for data frame, and then messes up, let's say, and assigns a series to a DF variable, then our classifier should flag it as a warning. Okay. So yeah. Thanks.
Okay. Thanks a lot. Any other question from the audience? Okay, then I'm really curious about the automatic proof generation. So this is Emily. Okay, so in this case, so I may have missed this from the talk, but basically what you're doing is to use machine learning to automatize the proof search. So how much does this work for the full proof? So you can generate the entire proof automatically, and how much this is still interactive? So like it suggests the next step, but then there is always a human in the loop.
Yes. So in our case, we take the human out of the loop for the generating of the proof script. So it predicts that the model predicts the next tactic. We kind of query the model to predict the top K tactics that it could be. And then you can do like depth first search and try and synthesize the proof. So you do it until you get to QED or until you time out and you don't end up generating something.
Mm-hmm. And this is done for Coq. So it's really the proof
yes.
code that you are, okay. And so I was wondering, because at the beginning you had this distinction between like proof languages and implementation languages, and Coq is very much on the side of proof languages.
Yeah, so you can also implement the code that you want to be proving in Coq. So that's what you would kind of have to do. So you want to implement a compiler, you write it in Coq, and then you also use Coq to prove it. There are ways that you can take something from another language and maybe translate it over and then try and prove things about it. But
I was thinking more at languages that are a bit more on the side of the programming language rather than theorem proof, things like Agda or Idris. How would that look like? Yeah.
So our approach would work for anything that has this sort of tactic language. So when you write a proof script, what's actually happening in Coq is that when you execute it, Coq is using those tactics that you've given it to try and find a proof in its underlying language called Galena. And so what we do is we just look at the proof script, so this high-level tactic language, and we predict proof steps from that language.
So I'm not very familiar with Isabelle, but people that I know that have been using Isabelle for a while, when they move to Coq, they complain that it's less automated. So that they were used to better automated proof search in Isabelle.
Yeah, I'd say also.
Yeah.
So there are some tactics themselves that like they're either built in or custom tactics that sort of take some of the steps out of the way. And so if your model is able to predict those tactics, then great. But if not, maybe you could have a human in the loop that knows the tactic to use and would try that as like a first try.
Okay. Any other question? I feel like I'm having all the fun here.
Maybe I can follow up on this discussion. I was wondering how so you have several strategies for searching that you mix up and try. I couldn't figure out if that means that you're trying them depth first, breadth first, trying each one a little bit and going forward on all of them to see how it works, or you're combining it in the same proof. You use one kind of strategy and then switch to a different one, but in a depth first manner. How does that work?
Yeah, so what's happening is essentially we have multiple models, and they are performing their own depth first search. So the searches are all separate, and let's say we have a particular theorem that we want to prove. We can say, okay, all these models, try your own search, try and find a proof of that theorem, and then whichever one ends up producing the proof script, then we take that completed proof script.
Okay, so you're not combining at all.
No, so
Can
the
I
only
check-
time, yeah, you can.
Right, I just wanted to add a little bit of depth, not depth, what's the right word? A little bit of insight into why this diversity thing works with things. So what we find is that, imagine that you have a model that you've built. You take a bunch of proofs and you throw it in and you try to learn a language model. It's going to, given partial proof, predict what's the next tactic. And so imagine that in learning this model, you tell it, only look at the last 2 steps of the proof when you're trying to learn what the next step is, right? This turns out, almost shockingly, is actually good enough to be able to proofs. Now imagine you build another model, and this one you say, look at the last 30 steps. So look very deep into the proof to try to predict the next step. It turns out that very often, this kind of model proves a very different kind of proof. So it's unsuccessful on some of the things that the 2-depth model was able to prove, but it's successful on different kinds of theorems that you're trying to prove. And so the question is, how can you build the best of all worlds? How can you take a bunch of these different models that all look a little different and make different predictions, but they seem to be successful in different kinds of theorems, right? And so that's what this diversity thing is really about, is we're making a bunch of different models. They're all doing their own searches, just as Emily said. And then there's this trick that you just mentioned briefly, that you can do one search a little bit and then do another search a little bit and then do another search a little bit. And you kind of do this depth first searches. And with that, you can actually do it really, really fast. You can run through a lot of different searches faster than you would run a single one all the way to the end. And you end up accelerating the construction of the proof by 97 pretty dramatically.
If you look at a proof that is automatically generated, do you spot that it wasn't a proof done by a human? How different is it? How is it any readable? Is it?
So it's still readable because it is in this higher level tactic language, but our proofs do look a little different. So a couple times maybe it gets stuck in a little bit of a loop that a human obviously wouldn't be doing. And it could sometimes be a little longer. But yeah, at least it's proven sometimes.
I think it would be really interesting to look at that from that angle, right? How do these proofs look like compared to the proofs that a human would generate? Yeah. All right. Any question for Ellen? So I have one. So in your talk, at some point you talk about, did I get it right? File systems. Is that correct? So how come file systems and JavaScript? That's something I missed. So.
Oh, sorry. So yeah, so it's just libraries that are built for interacting with the file system. So stuff like reading and writing files, reading directories. I guess I should have maybe put a little bit more intro to JavaScript, but I know commonly people think, oh, it's only for websites, but there's actually a lot of server-side JavaScript. And so reading and writing files is pretty common functionality that you want.
And so do you also need to generate a stub for the callback also, or?
Like, what do you mean?
So what is the test? How does the test case that you generate look like?
Oh, well, so I showed the test that we built up at the end.
Yeah.
So I guess there's a little bit more infrastructure that happens before I generate any of the tests. I'll generate like a toy file system essentially, so that when you are generating calls to like a read and write file, there's valid inputs that exist. So essentially, like when you're choosing strings for the string arguments that are randomly generated, they will correspond to like file paths in this toy file system that I built.
ask a question to Alan?
Mhm.
So, what kind of feedbacks do you provide during the test generation? So,
Oh yes, good question. Yeah, so so basically the I guess the base level thing is the callback executed or not? Because if the callback is executed, that means that you can extend the test inside of the callback. But other feedback includes like, did the test crash? Because if the test crashed, then it's not a valid test to extend. Also, I was outputting the values of the arguments and the returns for all of the calls to everything. That wasn't used as feedback for the test generation itself, but then that is how we did. You probably don't remember, but one of our research question was how many behavioral differences can we find with these generated tests? And so the detection of behavioral differences was in terms of, okay, does the callback argument change? Or like, is there a different return to a function call? And so we were also outputting all that feedback in order to be able to compare between executions.
But wouldn't, if you don't give that feedback, wouldn't that make the same test getting generated over and over again? Like
No.
duplicates. So do you avoid duplicates by any way?
Well, not explicitly. So there's obviously like a random component to the test generation. But what we do is basically you start with this huge list of existing like the functions right in the API. Once we've generated a test for one, it's like in a weighted map. So the odds of choosing the same function again will decrease. So, you're not going to end up with only testing the same function over and over again. The map is designed such that, if the stats work out, you're going to end up testing all of the APIs in the library. And another thing is that we were doing our tests on 1,000 tests, and none of the APIs had more than 100 functions. So, even if you do get a couple duplicate calls, you're going to end up testing pretty much all the functions. And then also the arguments are random. So you can have multiple calls to the same function with different arguments and have different results.
And is there a limit to the type of arguments that you produce, like only primitives, or do you also generate any type of argument for those?
Yeah, so the type search is the classic Java primitive. So strings, numbers, booleans. We also did, the callback arguments, right? That was kind of the point. We could pass in other function arguments. So those were mostly functions that were part of the API already, and we did randomly generate objects and arrays. So those are all the types.
Do you think there is anything specific to JavaScript? So why JavaScript? Because it was convenient to test and there was a lot of code available, or because callback based interfaces are everywhere, right? So you could probably
Well, the interesting thing about JavaScript is that because it's a dynamic language, you don't have really any information available statically. So figuring out what the signatures are for the API functions, that's kind of a hard problem in JavaScript. So this kind of stuff's in the paper, but one of the examples that we found that was kind of interesting is that in JavaScript, you can call any function with any number of arguments. And if it takes more arguments than it's supposed to take, then I'll just ignore the last arguments. So figuring out this is a valid way to call the function. Like, you don't get an error if you call it with garbage. Most of the time you just, it either just runs normally or it'll return undefined, which is basically like null. But yeah, the error detection is hard. So that's kind of what makes it interesting. The other thing that's kind of nice is that the way that the callbacks work is the way that you do most asynchronous programming in JavaScript, but JavaScript is a single-threaded language. So that does remove a lot of the complexity that you might have in other languages where you have like multiple threads that might be interacting, they might have shared memory, they might not. So in this case, it's really just like, okay, the JavaScript is running in a single-threaded way, and then it'll dispatch computations such as a file read that'll happen kind of in the background because it's calling like the operating system. But yeah, it's just a lot easier that way.
Any other burning question? We have 1 minute left in the section. All right. If not, well, you know how to reach out the authors anyway. Let's